we proceed in this lecture from where we have stopped in the last lecture. So, we have discussed about the diode, how the PN junction is formed, how the barrier potential is developed, and this barrier potential leads to two very different phenomenon of forward biasing and reverse biasing of the diode. So, we understood that during forward bias condition, the majority carriers will be able to drive a current through the device. They will be the carriers for developing that current. So, to have that current within the device, and that is a large amount of current compared to the minority carriers. Obviously, when we will see see the level of currents we are talking about, they will basically be in milliamps. So, we are when we say large current, we think that it is in amperes or kiloamperes like that, but in electronics, in the purview of electronics, milliamps to amps, 1 amp range is quite large enough. So, we are talking about large current in the range of milliamps, and the minority carriers would contribute to current in the range of nanoamperes to microamperes at the best. So, they are very negligible, and we also understood that these minority carriers will give rise to something called the reverse saturation current when we have reverse bias the diode. I told you to read the reverse saturation current from the book, so you should have read it, and this is the current due to the minority carriers alone. So, the minority carriers is always present, and we know that in whichever way you bias the crystal, the minority carriers will be able to drive a current. So, this is the reverse saturation current created by the minority carriers. So, that we also talked about, but it is very negligible. It is in the range of nanoamperes, and we can nanoampere to microamperes at the best, and for all practical purposes we can neglect this amount of current. So, we can consider that the reverse bias is giving rise to a situation as if the circuit is open, that is no current is flowing through the diode. So, today we go ahead from here, and I will start sharing the screen. So, I hope you are able to see the whiteboard. So, first we discuss something called the diode equation. This is also called the Shockley equation. So, the name of this equation is Shockley's equation. What does it give? It gives the relationship between the diode current ID and the diode voltage VD. And you have the ID coming from the VD. So, we are giving certain voltage across the diode, that is the bias voltage. The VD is the applied, here it is forward bias voltage across the diode. So, we are talking about forward bias region actually for the Shockley's equation. So, it is the forward bias voltage applied across the diode, and there are several other parameters as you can see. First, let us discuss VT. So, VT is here. What is VT? VT is KTK by Q. K is Boltzmann constant, it is a constant in physics. Tk is the absolute temperature in Kelvin, and Q is the electronic charge. So, this gives rise to this VT, and if you calculate for 25 degrees centigrade, if someone has their calculators, their scientific calculators ready by the side, they can verify that this will come out to be 26 millivolt, near about 26 millivolt. Okay. So this value you may remember as Vt as 26 millivolt, because otherwise you have to remember the Boltzmann constant, which we generally don't remember actually, but Q we remember, and Tk is the in Kelvin's temperature, so you can calculate also, but you can directly remember that at 25 degrees centigrade it is 26 millivolt. Okay. And for other temperatures you can like have a ratio done for Vt, what the different Vt will be for another temperature. So it is a very direct relationship with the temperature, as you can see. And what is N? N is 1 for germanium and 2 for silicon. So you can remember these values. N is 1 for germanium and 2 for silicon. So when you know all this N and Vt, then you would be able to calculate Id based on Vd. But another thing you need to know the Is, the reverse saturation current, and this reverse saturation current will be generally given to you because this is specific to a particular diode. This is specific to a particular diode and it does not change. When the diode changes, it changes, but for a particular diode the reverse saturation current is same, and this is given in the data sheet. So you see diode specification sheet in the right hand side, you see the Is is also mentioned here in point 3. The reverse saturation current is specified. Okay, the reverse saturation current is specified in a diode data sheet. So with all these values known now, it is a relationship between the voltage and the current in the diode, the voltage across the diode and the current that you get when you apply that voltage. So as you can see, this is a highly nonlinear equation. So as I already told you that we would now start seeing elements which are not linear in nature. So the relationship between the Vd and Id, or the V and I graph, will not be linear anymore. So we have, this is the first instant where we are facing this nonlinearity. Okay, this nonlinearity we are facing. So where from this Shockley's equation is coming? So we don't answer this question in this course. It is coming from some complicated solid state physics. So this equation is given to us from the physics of semiconductor. So we work with this equation, and as you will see going ahead, we also generally don't work with this equation. We adopt more simplified approaches called approximation. So we approximate the behavior of the diode. So this Shockley's equation gives the behavior of the diode, but we don't utilize the Shockley's equation so often, and we approximate this equation, or we approximate the behavior of the diode to certain forms which are more suitable to us to work with. We would see all that also in this particular lecture only. So let us move ahead. I urge you to read the diode specification sheet part from the book for details. So this book from where I have taken this is a Boylestad book. Okay, so this is the Boylestad edition 11. So these are available in internet also, and I had also shared, if I remember correctly. So this book also I have shared, so you can see the section number 1.12. so you can we can read from there in details, and if you don't understand anything from there, you can ask me. I will try to explain that in the next lecture. So these are not so important for our numerical calculations, so but for understanding the diode it is useful to know all these things when you actually start working with the diode. So since we are also not doing the practicals this session, so I am not going into this in so much detail. Now let us go into the symbolism of the diode and how the diode characteristics look. What is characteristics? Characteristics is the relationship between the different variables which are associated with a particular device. In this particular device called diode, the variables are the applied bias voltage and the current through the device. So, ID and VD are the different variables. So, the relationship between ID and VD is the diode characteristics. So, as you can see, the Shockley's equation gives the diode characteristics in a mathematical formula. However, we can also draw this, we can draw this formula also. So, you know how to plot a formula, and also you can do an actual experiment, and this is one of the experiments that you would have done if you had done the laboratory. So, this is the first experiment that we do. We plot the diode characteristics curve. So, how do we do that? It is very simple. We apply a forward bias voltage to the diode. So, we have a battery connected to the diode in series with a current limiting resistor, so that we don't burn up the diode. So, that because you see that there is a maximum forward current also as a specification. In the specification number 2 you read that there is a maximum forward current. So, we should not exceed that current. So, to ensure that, we connect a high resistance in series with the diode and then apply the voltage, then connect the diode to the circuit. So, when we increase the voltage across the diode, we also get a current in the circuit. So, we take note of these two values, the VD and the ID, and then plot the characteristics. When we plot the characteristics, we will get a shape like this. We will get a shape like what you are seeing in the right hand side right now in black. In black, what you are seeing is the diode characteristics in the forward bias region, and this is the diode characteristics in the reverse bias region. And now you can very easily understand what behavior we had discussed in the earlier classes exactly matches with these characteristics. Let us understand in the forward bias, as you had learned, that till a certain voltage, which is the barrier potential, there would not be any flow of current in the diode. Now, you see here, till it is 0.7 volt, the current is 0. You can consider it 0. It rises a bit from a certain point before 0.7 volt, and it goes up. So, after 0.7 volt, it rises up very quickly. So, the current is very large after the barrier potential is crossed. Okay. So, this particular plot gives rise to this sort of a diagram, and here this juncture is known as the knee. So, this knee term is coming from actually terminologies related to graphs and plots. So, knee is a place where the curve like bends suddenly or changes abruptly. So, that point is called the knee point, knee region. So, that is why this barrier potential is also called the knee voltage. So, you will come across this term knee voltage when you are reading from the textbook. So, I mention this here. So, that is called the knee voltage. So, the knee voltage is nothing but the barrier potential. So, it is 0.7 volt for silicon crystals. So, after the knee voltage is crossed, as you had already learned that the current will increase dramatically, and it rises in an exponential. It rises in an exponential. You can see from the Shockley's equation, the rise is exponential in nature. When VD is with VD, the current is increasing exponentially, but it is increasing after 0.7 volt is crossed. So, this is a forward bias region. What happens in the reverse bias region? In the reverse bias, only a reverse saturation current is there, which is very small. As you can see, this black line is very close to the 0, is very close to the horizontal axis. So, a reverse saturation current takes flows in the reverse bias condition. So this is the diode characteristics, and so we had explained that, and this is the symbology of the diode in the left hand side. So you see this a triangle with a wall sort of thing is a diode. So you don't need to fill up the triangle as shown in the in this picture. This triangle can be like left unfilled, so it is fine. What I have drawn is fine, absolutely fine. So now if you connect a voltage like this, this is a forward bias. Now which end is the P end and which end is the N end, you need to understand.
Left hand is P.
Yes, this triangle is basically giving you the direction of the forward bias current. So this triangle is you can consider that as an arrow. So this arrow is basically giving you the direction of the forward bias current if the diode is biased appropriately. So that would mean that the battery positive potential, that would mean that this is the P side and this is the N side, and the battery potential positive potential should be connected in this side and the negative should be in this side to make it a forward bias. And when it is reverse bias, then you simply reverse this. Either you change the direction of the diode or you change the direction of the battery. So this is also a diode, okay. In this way you can also draw it. This is also a diode. In this case, this is the P side, this is the N side, and this would be forward bias. This is forward bias now, this is reverse. So this is the thing, this is the case. Now as you can see from the characteristics, if you idealize this, if you idealize these characteristics, it is almost behaving in a way that when we have a forward bias diode, there is a current flowing through the diode, and when we have a reverse bias, we don't have a current flowing through the diode. So it is almost like a mechanical switch. When the switch is on, there is a current flowing through the switch. When the switch is off, there is no current flowing through the switch. The diode is basically approximated as an ideal switch. The diode is approximated as an ideal switch. This is a very important phenomenon, and this gives rise to all different applications that we would see in electronics. So please remember this very well. So everyone will remember this for your lifetime, I am very sure. Even if you don't remember anything about diode, you will remember that diode can be used as a electronic switch. When you forward bias, it is on; when you reverse bias, it is off. This much you will remember for your lifetime. Okay. So but there is a fundamental difference between a switch and the diode. The difference is this, that when a switch is on, current can flow in any direction, in both direction. However, when the diode is on, current can flow only in one direction, only from the P side to N side. Current cannot flow in the opposite direction. So this is the fundamental difference. But that is fine with us, we work with that limitation, we design our circuits in that way only. But the other important thing is this, that when we utilize this ideal behavior of the diode, then we get this blue line which you see in the right hand side now, this blue line as the ideal characteristics. Ideal characteristics. Previous one was the actual characteristics given by Shockley. This is the ideal characteristics which you can simply plot, because you know that when it is on, that is it is 0, it is passing like it has crossed 0 voltage, it is on, in the forward region it is on. So there is any current that you wish, you can pass through this diode, and when it is in the reverse bias, when the voltage is less than 0, there is always there is 0 current. So everywhere in the reverse bias region the current is 0, and when it is just above 0, or you can say it is 0, the current, that it is any current you can pass through it, and since it is a switch, the voltage across it would be 0. So this is an ideal case. So we know that there would be a 0.7 volt drop across the diode even in the forward bias, but when we are idealizing this as a switch, then there is no voltage drop points of 0.7 volt. The voltage across a switch we know is 0. So that is why we also draw it like a ideal case, a straight line in the vertical axis. So when we know about all these things, so the ideal characteristics and the actual characteristics, now we go ahead to understand the diode resistances. So there are several types of resistance that we would encounter now. Why? Because we are seeing a nonlinear device. So in a linear device, all these resistances that I am defining all become equal. You would very well understand as you go through these definitions why they become equal in linear devices, but they are different in nonlinear devices. So the first one is DC or static resistance. This is very easy. It is simply a ratio of the bias voltage to the current. So it is simply Vd by Id. So there is an operating point. Suppose here there is the operating point. This is called the Q point. I would define it more in later. So this is called the Q point, the operating point. So at the Q point, the voltage is Vd and Id. So this should be capital D, as I have written in the equation, Vd and Id. So this is the static resistance, very easy, is simply simple ratio. Then the average AC resistance. So suppose we are having a range of voltage, a change in the voltage applied across the diode, which is delta Vd. About the operating point, we have a change in the bias voltage. Suppose a AC voltage is getting acted over that region. So all are in the positive side anyway, and that is giving rise to a change in the current also in the diode. The current range change is this delta Id. So this R average, which is the average AC resistance, will be delta Vd by delta Id. So suppose that, let us do a quick example here. Suppose this Vd is 2, this is 2, and maybe this is like 10 milliampere suppose. Then what would be this? This would be 2 by 10 into the power of
200
minus
ohms.
3.
0.5 kilo ohms.
0.5 kilo ohms, as someone has told me. I am not verifying yet, it is correct, it seems. And suppose this,
It will be 0.2 kilo ohms or 0.2.
0.2, yeah, not 0.5, right,
200 ohms.
0.2. And suppose we have this change in voltage as 0.1 volt each side, okay. Then delta Vd would be 0.2, and
0.2.
suppose this has become this is 9.8 milliamp and this may be 10.4 milliamp. Then the range is 0.6, let us not complicate things so much, 10.3, so this is 0.5. So you get this is milliamp of course, and this is volt. So what you are getting is 4 something.
0.4 kilo.
0.4.
0.4 kilo ohm. Okay. As you can understand, as we move downwards in these characteristics, the resistance, both this type of resistances will increase in value, and as we move in about this slope higher, these resistances will decrease in value. Okay. I hope that is quite clear to you, because you know basic
Yes, sir.
of this basics of this graphs and all.
Slope of the graph.
Yeah, slope of the graph. So slope of the graph is increasing, and the resistance is basically the inverse of the slope.
Resistance is, sir.
The resistance is inverse of the slope, because this is I, this is V. Okay. Now you see there is another which is called the dynamic resistance, the AC resistance of the dynamic resistance. Here this delta VD and delta ID needs to be very small. So this cannot be very large, maybe more small, might 0.01 volt or something like that, and then a very small change in the current will also be there. Then you can take the ratio. But as you can see, this basically is a definition of the slope of the curve at this operating point. When we define this delta as very small changes, then we are basically trying to talk about the slope of the curve. So this is the slope of the curve we are trying to talk about. Okay. So this slope of the curve, as we know, is given by the derivative dVd dId. So dVd dId, we have the Shockley's equation when we are working in the forward bias region. We have the Shockley's equation with us, which gives the Id with respect to Vd. So we differentiate with respect to Vd in both sides. So we get dId dVd, and in this side it will come out as this. And then we have some approximation we can do to simplify. We do not need to do an approximation anymore. We can simply invert this and we get the AC resistance, but we have terms like Is here involved. So if you do not know the Is, then you can approximate in this manner, that in the forward bias region Id is much greater than Is, so you can neglect the Is compared to Id. So you can simply write Id and then invert, and when you are inverting it becomes NVT by Id, and this NVT we have already seen that in room temperature it is 26 millivolt approximately. So RD can be directly calculated as 26 millivolt divided by Id, the operating current you need to know. So since you know the operating point, the current here in this particular example is 10 milliampere in this operating point. So the AC resistance would be 26 millivolt by 10 milliamperes. So this is 2.6 ohm that you are getting. So this sort of simple numericals may come if you are given a graph, if you are given a proper graph where you can actually figure out all these points from the graph itself, you can calculate these resistances. Okay. Otherwise, yeah.
Sir, ID and IS, what is the difference in both these currents?
ID is the current through the diode. IS is the reverse saturation current. Now ID is always changing. As you keep on changing the bias across the diode, the current through the diode will also change. Okay, it has a relationship with Vd, the bias voltage. But the reverse saturation current is the current when you have, this is specific to a particular diode. When you apply a reverse bias, then there are only minority carriers which are contributing to the current. So this minority carrier current is called the reverse saturation current. In the forward bias region also the reverse, the minority carriers are there, but their contribution you are not able to visualize separately. When you make it reverse bias, then only the reverse saturation current is present. So whatever you measure during reverse bias condition is the reverse saturation current, and that will remain constant throughout the reverse bias region. Okay, so that is specific to the particular diode. It comes from the diode data sheet. The manufacturer will give you the reverse saturation current, and you can verify it also by putting the diode in reverse bias. You will be able to measure that current. So this is about the resistances, different resistances. So you can calculate these resistances if you know the VD ID values, or the delta VD and delta ID. You can know that from the graph if you are given an operating point, or later on you would be able to calculate these VD, ID, etc. from a circuit itself. So when you will be able to calculate that from a circuit, then also you can calculate these resistances by knowing these values of VD, ID, etc. Now you see, next part of our lecture is the load line analysis. So we know the characteristics of a diode, but what happens when this diode is inserted in a circuit? So first time we are now inserting a diode in an actual electrical circuit, and trying to understand what we would have as the solution of the circuit. What do we mean by solution of a circuit? Solution of a circuit means the different voltage drops across different elements in the circuit, and the different currents flowing through the different elements in the circuit. Voltage and current, this is all in electrical engineering. But why things become varied? Because there are varied elements, varied devices. There are all sorts of complicated circuits you can imagine, that you can draw, you can make. So you have solving the circuit would mean that you need to know the voltage drop across each of the elements and the current flowing through that element for all the elements present in the particular circuit that you have designed. Then you are solving the circuit. So here we are trying to solve the circuit by something called the load line analysis, which is very like a typical type of analysis for non-linear devices present in a circuit. What we are trying to see is that you know what is the philosophy. Try to understand the philosophy here for the load line analysis. So in this particular circuit, this is a very simple series circuit with a diode in the circuit. So in this circuit, the diode will always behave as per the diode characteristics shown in the blue in the right hand side. The diode's VD and ID will always follow these characteristics. It is as if a law of the diode's own law, the Shockley's equation. The VD and ID cannot move apart from this line. However, there is another law governing the entire circuit, and that law is more fundamental, which we have learned that is KVL, which we have learned in a very first lecture probably of electrical engineering, which is the Kirchhoff's voltage law, and there is associated current law also, but in this case we would be utilizing the voltage law only. This governs any circuit, whatever complexity might there be in the circuit. KVL and KCL are always applicable, so it is more fundamental. So you always remember that these two tools are always there to help you out. So we apply the KVL here, and when we apply the KVL, we see E minus VD minus VR equals to 0. E minus VD minus VR equals to 0 is always true. So this has to be true, as well as this characteristics has to be true. both things are true at the same time in this particular circuit. And this KVL, this VR, we can write as ID into R. When we write it like this, VD ID plot is nothing but a straight line plot. I hope you understand this. VD ID relationship is nothing but a straight line. And so that means that in this plot VDID, there is a diode characteristic plot as well as a straight line which is governing the entire circuit, and both are true. That means the intersection of these two plots would give you the operating current and voltage in this circuit. The operating current and voltage in this circuit. You get the point? Why the intersection is giving you the operating voltage and current? Because both the straight line and the diode characteristics are coming from two different laws which are true in this circuit. So both these need to be
Both the
set.
laws are followed.
Huh?
Both the laws should be followed at
Both the laws should be followed at the same time.
the intersection point will.
Yes, the intersection point is the point where both the laws are being followed at the same time. So that's why we get the intersection point. And now the task is to draw this line in this plot. So it's very easy to draw this line. So we take one point where VD is 0. When VD is 0, we have ID equals to E by R. And when we take another point in the vertical axis, in the horizontal axis where ID is 0, and we get VD is equals to E. You see this point is E and this point is E by R. And what is the slope of this line? The slope of this line is basically 1 by R, right? This thing.
Yes, sir.
So the slope is E by R by E, that is 1 by R. So this slope 1 by R. So when you know the load resistance connected, you can immediately draw this line. Also by knowing the E value and the R value, you will be able to draw this line. So in either way you will be able to draw this line, and this line will intersect the diode characteristic plot at a particular point which is called the Q point. Q point is short for quiescent point. I hope I am correct in the spelling. Quiescent point, you check it from the textbook. Quiescent point, quiescent means unmoving. Quiescent in some language means unmoving. So this is the unmoving point of the total circuit. That means this is the solution of the circuit. The circuit operates at this point. It does not move away. It is unable to move away from this point as long as all the other different parameters of the circuit are what they are. So this R, if the R changes, of course the Q point will change, but for the same R, for the same E, and for the same diode, the Q point will be this. You take the circuit out and place it from, suppose this circuit is made in Roorkee, this circuit is made in your where you are living, this circuit is made at anywhere on earth or anywhere in the universe, the Q point will be this only. It cannot be something else. That's why this is called a fixed point, is the an unmoving point or Q point. Okay. Once you change anything in the circuit, yeah.
It means that there would be a specific value of ID and VD.
Right.
For that circuit.
Right, and that is this IDQ and VDQ. Now you will be able to plot out from this, you will be able to figure out from this plot, from this intersection point. Okay. Of course this has to be in scale, so all the different you should be able to figure out from the plot then you would know the VD and the ID at the Q point. This is getting called as VDQ and IDQ. Okay. So, this is the load line analysis. The load line analysis can only be done when you are given with a characteristic plot, otherwise you will not be able to do it. Okay. When you are given a characteristic plot, then you would be able to impose the straight line for the network, this line with the slope 1 by r. This line you will be able to draw on this plot, and you will be able to figure out the Q point. So, this is one sort of analysis called the load line analysis. Now, we move ahead to the most important part of the diode, which would help us solve circuits of a more general nature. As you can see, this load line analysis, in this load line analysis, we have a series circuit only. A series circuit would mean, in another way, how to generalize a series circuit? It would mean that you know the load, this is the load which is connected to the diode, and you know this potential that is getting applied from a connected network. So, there can be a very complicated network in this side. However, you should only know the voltage that gets at these 2 points, that gets across these 2 points applied from the network. That voltage you can consider as E. So, you have not read probably the Thevenin's equivalent circuit and all. So, when you know all these things, Thevenin's theorem, then you will appreciate that how a longer network, a more complicated network can also be utilized for load line analysis. In that case, this E would come from the network and you would be able to calculate it by utilizing Thevenin's theorem, and this is the load R that is connected with along with the diode. So, anyway, we are not going into much detail there. So, in the limit of what we are discussing, so this load line analysis can be applied for this sort of series circuit only, but we know we have to deal with much complicated circuits. So, in that case, we would have to shift away from the actual characteristics of the diode, because otherwise what would happen? Otherwise, we have to solve the Shockley's equation every time, and that solving the Shockley's equation, okay, let me point out one thing. In this particular series circuit, along with this KVL, the other truth, as I pointed out, is this diode characteristics, which is nothing but the Shockley's equation. So, you are basically solving the KVL as well as the Shockley's equation at the same time. So, you are solving a non-linear equation and a linear equation. So, the solution would become complicated because of the non-linearity in the Shockley's equation. For a simple series circuit, we can use the load line analysis, but for more complicated circuits, we cannot use this load line analysis, and we ideally or in actual situations we would have to use the Shockley's equation and all the other equations arising from the circuit, and then solve all these equations simultaneously to get the solution. However, that makes our life complicated, and we are not here to deal with so accurate solutions, because we are engineers and a few very milliamperes here and there does not bother us. So, we apply our common sense and we reduce the actual characteristics of the diode into approximate characteristics, which help us to solve the circuits in a very easier manner by utilizing equations only, not going into this sort of graphical approach of load line analysis. Simply by equations we would be able to solve, but there we approximate the Shockley's equations into some manageable approximations. Now, what are these manageable approximations? There are 3 different approximations that we utilize. So these three approximations you have to remember very well when you are dealing with diode circuits. This first approximation is the ideal approximation or as the ideal device. This is the 1, this is the 2, this is the 3 actually. This is the first approximation where we consider the diode as an ideal switch. In this ideal switch, when we can consider when the resistance of the connected network with the diode is much more than the average AC resistance, and normally you already have seen the AC resistance is very low, right, from the example that we have just done. So AC resistance is very low, so normally this can be considered that the diode is an ideal device. As well as the E network, there is a voltage connected voltage coming from the network is much greater than the knee voltage, and knee voltage you know it is 0.7 volt. So unless the voltage from the network is in the range of 1 volt or 2 volt, if it is much more than that, even like more than 5 volts, you can consider this diode to be an ideal device. So when we consider the diode to be an ideal device, we work with the ideal characteristics which we already have seen, and in the ideal characteristics the voltage across the diode is 0 and the current can be anything that is now getting decided by the rest of the circuit. So let us quickly do a very brief example. You see the textbook for many numericals which are already solved and many numericals which are given to you to solve. So for your own practice, you do those things, you do a few at least before coming to the tutorial, otherwise you will be lost in the tutorial. So suppose we have a 10 volt here and this is 10 kilo ohm. So typically these resistances which are connected to diodes are in the range of kilo ohms, because otherwise the current through the diode will be more than like milliampere ranges. So we want to limit this to some values which are in milliampere. This is set by the maximum forward current through the diode. So as you can understand that this diode is in forward bias condition and the current will be flowing through this circuit. What is the current we need to find out? So if you apply the ideal characteristics of the ideal approximation, then this I would be simply 10 by 10, which is 1 milliampere. Simply this, because the voltage drop across the diode is 0 now. Okay, if we had instead of 10 we had 20, then the current would simply become 2 milliamperes. See the characteristics, any current value is possible. Okay, so it only depends on what you have given in the circuit as your voltage and or as your load. Now come to the second approximation, which is called the simplified model or the second approximation. In the second approximation we include the drop across the diode. We include the drop across the diode, which is 0.7 volts, that knee potential or the knee voltage, that we include. So in this case, in this situation, the E network is not that large than the Vk, it is quite in the range of Vk probably, but the average AC resistance is quite less. Then you can apply this particular approximation. In this case, let us change this or let us make it remain in this manner only. So for the simplified case, your I would be 10 minus 0.7 volt. As you can see, a Vk has to be given here. So the 10 volt is here. Okay, 10 volt is here. So the potential across the diode is 10 minus Vk, 10 minus 0.7, and the Vk is 0.7 for silicon devices, and the and this is here now 10 kilo ohm, 10 kilo ohm. So whatever this value would come, can anyone?
0.93.
Yeah, 0.93.
0.93 milliampere. As you can see, when you have 10 volt here, having this simplified approximation and the ideal approximation, not much difference between the calculated values of current. Okay. Piecewise linear model, the next approximation, which is called the third approximation, piecewise linear model. In this case, the resistance is also considered. So you cannot consider the resistance of the network to be much more than the R average. So you consider there is an R average, and when you consider an R average, it is simply a straight line with the slope as inverse of R average, that much only. Okay, simply a straight line like this. So this is the third approximation characteristics of the piecewise linear model. In this case, this diode has to be replaced. Okay, let me I have not done one thing. When we are using the simplified model, then the diode, this part which was just like this in the ideal characteristics, would now become like this in the simplified model. This is plus minus Vk, and this is your thing, and here it is 0 volt. Okay, this across this it is 0 volt. So now you can solve the circuit very easily, and when you are using the piecewise linear model, then the same circuit that you see here, the diode has to be replaced like this. This is plus minus Vk, this is the RAV, and this is the diode. Here it is, there is no voltage, no resistance in this symbol. Okay. So additional resistance and potential drop has been introduced in the third approximation. So now you calculate what would be your I. Your I would be, you see
10 minus K.
yes, 10 minus 0.7 divided by 10 kilo ohm
10
plus
plus RAV.
this RAV. Now this RAV was, in our example, it was around 2.6, I think, right? 2.6 ohm.
Yes, sir.
So what is coming out? This is in volt. What is coming out?
Point 9299.
0.9299 milliamperes. So you see, it was very strange for us to do this complication, because it did not change anything from the simplified model. Why it is so? Because you very well understand the R network is very large. The 10 kilo ohm is very large than 2.6 ohm. So the value, the change in the value will not be very appreciable. Okay, this is a piecewise linear. So when to apply which approximation has to be governed by these things, and in almost all cases we have a very large resistance connected to the diode in any case. So normally this third approximation is not utilized so much, but you have to remember that in certain cases you might have to utilize it. Mostly this simplified approximation or the second approximation is utilized in most cases, but still so in many cases the ideal approximation is what we utilize. Simply it is either on or off, that's all. Okay, but in most cases we understand that it is on with an offset voltage, with some offset voltage is there. Okay, but this piecewise linear mostly we don't deal with that. Okay, but you remember this also, because in some problem you might see that this resistance connected is very less, so at that time you have to utilize this RAV also. Okay, and you will notice that appreciable changes when you include RAV and when you don't include RAV. So please practice some examples from the book. Boylsted has many different problems. Also the Malvino book also has problems. So you practice from any of these, and then in the tutorial you will not face any problem. So next week we will carry forward. There are some more things to be discussed on diode, some things like Zoner diode and all. So I thought we could cover, but let us not go into that now. So Zoner and some special diodes are there, and then important chapter is there for different sorts of circuits with new behaviors with the use of diodes. So we will see different new types of circuits with the help of diodes. So that with that chapter the diode part will end for this course, and it is very important you take time to understand the diode. Understanding the diode, understanding the junction phenomenon that is happening is important, is central to understanding electronics. Once you understand how the junction, PN junction behaves, you will understand the electronics on your own. So that is the core thing, that is the central thing that you should spend your time to understand. If you are not understanding, don't worry, we take time to understand a critical thing, but what we need to do is to stay with that, to not leave it. So you are not understanding the junction today, you look at it again tomorrow, look at it again day after, and you will understand. Eventually you will understand. Okay, you consult with your friends, try to understand from a different perspective, but try to understand how the junction behaves. If you are confident with the junction phenomenon, you would have confidence in electronics very easily. All these things that you are seeing, what we are doing, all are arising from the very basic phenomenon of the junction, PN junction. Only because of these, all these things have come out. Okay, so please give some time to understanding that will build confidence also in you. Okay, so I end the lecture now. If you have any doubts, queries, please write to me. We don't have much time to discuss today, but there is a long gap now. Again, Tuesday is the class, so 3 days I will be having. If you have any doubts, you post me. By tomorrow I will be having 2 more days to go through all these doubts and come out with some suitable reply to help you understand from a new perspective, if it's possible for me also to do that. But if you have any doubts and queries, please write to me. Okay, thanks. So I will stop sharing now, and so sharing has already stopped or what? I don't know. Anyway, I will leave the meeting, so probably that would stop the sharing also. Okay, stop presenting. I found it. Okay, so thank you for being here with the in the course, and see you next day.